So in section 9.2, we're going to learn about series and convergence. Now, when you start adding up a list of terms, like we do here, when you add them up, you get a series. It's no longer a sequence. Sequence is when you just list them. A series is when you add them. So let's add up the first few terms here. So for instance, if I added up just the first one term, that'd be a 1. If I add up the first two terms, that'd be 1 plus 1/2 gives me 1.5 or 3/2. And so on. So we'll do, I think they asked us for S sub 1, S sub 2, S sub 3, 4, and 5. So let's finish these up. S sub 3 would be 1 plus 1/2 plus 1/4. So that'd be 1.75, which I think is 7/4. And I'm starting to run out of gas here on this stuff. S sub 4 would be the sum of the first four terms. 1 plus 1/2 plus 1/4 plus 1/6. So maybe we'll do this by hand, and then I'll show you, if you want, how you can do this on a graphing calculator. Now I'm going to kind of cheat a little bit here for part of this. So that's 1.5, 1.5 plus 0.25 plus 1 divided by 6. Now, that's all well and good if you give me an answer, if I wanted decimal answers, but typically I'm going to want fractions. So let's do this. Hit the math key, then enter twice, and this turns into 23/12. So that's looking good. Now, I'm going to cheat a little bit. S sub 5 is going to be S sub 4 plus what number? Plus 1/8. So let's take this and add 1 divided by 8. And it gives me this thing. Play the math, answer the fraction key, and I get 49/24. Yay. Okay. So that's my sequence of partial sums. And that's what these things are partial sums. Sum of the first n terms. S sub n, sequence of partial sums. Now, if you wanted to get your calculator to do stuff like this, or some of the stuff anyways, then it'd be helpful to have the general terms for this. We practiced that in the last section, but it doesn't hurt to work on this again. This is the first term, this is the second term, this is the third term, fourth term, fifth term. And, well, what do we got going here for the nth term? Well, this is 2 times 4. This is 2 times 3. This is 2 times 2. If you look carefully at this, you might just start to see a correspondence here. What would be the general term for this? 1 over what? Close. 2 times n minus 1. And you can distribute that. They can be 2n minus 2, etc. But 1 over 2n minus 1. Is that going to work? No, that's not quite going to work, is it? Because what's going to happen at 1, right? You want to put in a 1 here, that would give me a 0. That'd be a problem. So what's the general term here? 5 and a 4, 4 and a 3, 3 and a 2, 2 and a 1, 1 and a 0. I'm going to have to think of a different term than that then, I guess. What would be a 1/2? This isn't good. Maybe I shouldn't do this one on the graphing calculator then. Because we need to come up with the general term here. And my problem is that that general term is not going to work at n equal 1. What's under the arithmetic sequence? 1 over 1. I need to get a 1 here at n equal 1. So let's call that 1 over, no. We're going to have to come up with something different there. Well, 2n minus 1 would give us odd numbers if we did 1 over 2n minus 1. Is that what you're saying? That would give us all odd numbers. So 3, I'm not seeing how that works. I'm not sure why this one's so difficult. 1/2.
It's probably the one on the test.
Yeah. Yeah, that's a good test problem. We'll save that for that one. All right. Well, let me just demonstrate to you how we can set up certain sequences. And the notation for that is your sequence command, and then the expression that you're going to use for whatever your general term is, and we haven't figured it out for problem number 4 yet. That's all right. Sequence, expression, and then you type in the variable, and then your beginning term, and then your ending term, and then the increment. If it's something other than 1. So to find that off your calculator, you're going to hit the second button and then the stat button. Second and then stat. So let's do second and then stat. Second, stat. And let's see. If you cursor over to the right one, then the 5th option down will be sequence. So second, stat, and then cursor to the right one. So let's select that, and let's give ourselves something pretty friendly. Now, if you're not getting a menu-driven system like this, that's okay. You can still type in exactly what we're going to do. You're just going to have to put in commas. So let's say our expression is 1 divided by, let's do 2 to the nth. All right, let's do 2 raised to the x power in this case. The variable for us is going to be x. Let's start at, say, no, let's start at 2 and end at 5. And we'll go up in increments of 1. When you're ready, go all the way down to the bottom and press paste. It'll paste in the command that if you didn't have this menu, you would have to type in. So that's what your command should look like, regardless of whether or not you typed it in through a menu or just typed it in. You press that, and it gives you all of these values. Now, if you want to be fancy, you can hit the math key, answer the fraction, and it'll turn those into nice, neat fractions. And if you want to be really fancy, we can calculate the sum of these. So you go to second list, then over to ops. This time I want the sum. Now let's do the sum of my previous answer. So second and then the minus key, like that. So there you go. That's the sum of those 4 terms. I'm not sure you really want to spend too much time trying to play with that, but it is kind of handy for what it's worth. Let's focus on the task at hand, though, which is going to be working with this sequence of partial sums. You know what? I probably should have done that for problem number 6 here. Problem number 6 gives us something that is actually probably pretty ideally suited to this kind of work here. So it's the sum from n equals 1 to infinity of -1 to the n plus 1 over n factorial. So let's list a few things here. So the first term, when n equals 1. If n equals 1, I'll have a 1 factorial here and negative 1 squared. Now this summation notation, hopefully is something that you've seen before, college algebra and calc 1. So plus, and now I need to know what happens at n equal 2. At n equal 2, it's 2 factorial, negative 1 cubed, and so on. Always this exponent is going to be 1 more than the n in the factorial in the denominator. Now I'm just going to list out the first 5 terms because we're going to try and find the partial sums here. The last one I want to list out is negative 1 to the 6th power over 5 factorial. How do these things simplify? Well, the first one is just going to be 1. The second one, is your term in the second one going to be negative or positive? Negative. So it's going to be negative 1/2. Third is going to be positive 1. What's 3 factorial? 6. Good. Plus negative 1 over 4 factorial, which is 24. Plus 1 over 5 factorial, which is 120. So if I want to find these partial sums, I could probably do this with the calculator, but let's just do it by hand. It's not that hard of a problem. S sub 1 is 1. S sub 2 is 1/2. What about S sub 3? Well, it's just 1/2 plus the next term, which is 1/6. So let's kind of keep our little running total here. I've got 0.5 plus 1 divided by 6. Hit the math key, answer the fraction. Not that you didn't recognize this anyways, that's 2/3. S sub 4, keep the total going. Let's add negative 1/24. So minus 1 divided by 24. Two-thirds. 16. Yeah, okay, 15. Yeah, all right. That makes sense. So S sub 4 is 5/8. And the last one, S sub 5. So at some point you might reach a limit with what your calculator will turn into a fraction. So the last part, I'll add 1 divided by 120, answer the fraction, and I get 19 over 30. So this is my sequence of partial sums. So here, 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 here. What we'd like to see is, are these numbers closing in on something? Are they getting closer and closer to a particular value? If they are, great. If not, well, that's kind of a bummer. But we'd like to know what they're getting close to if they have some kind of a limit. So what would this add up to? That's a question we're going to answer. Not for this one, though. Right now, we're just trying to get used to the notation and expanding these things and understanding what the sequence of partial sums is. Are we okay with problem number 6? 4 and 6 here? Let's keep going with geometric series in general, which is going to be a big part of this section. So geometric series. Geometric series looks like this. You're going to start out with some term, call it a sub 1. And then to get from the first term to the next term, you're going to multiply by some number which is in a fixed ratio with everything else. So I'll multiply this by r, some ratio. If I multiply this one by r, then I get the next one. So r times r is r squared. Times by r again. This time I get a sub 1 times r cubed. And so on. And so the sum of this is your geometric series. Now, it could be a finite geometric series, meaning after a while they'll end, or it could be an infinite geometric series, meaning there is no end, that you're going to add that up all the way out to infinity. We can write this using our summation notation. So two possibilities. One is the sum from n equals 1 to, let's call it k, of a sub 1 times r to the n minus 1. So we're giving ourselves some kind of a finite limit. If you added up all these first terms, that limit would be this. A sub 1 times 1 minus r to the k power over 1 minus r. So you get a nice finite limit. We can also look at this case in the infinite limit. So let's do n equals 1 to infinity of a sub 1 times r to the n minus 1. Now what's nice about this is that the formula actually gets easier. In the infinite limit, this term, under the right conditions, is going to go to 0. So it's just going to be a sub 1 over 1 minus r. Now that's providing that r is less than 1 in absolute value. If that's true, this term is going to disappear, and we can calculate that infinite limit, that infinite sum. Okay. Let's practice with this a couple. We'll start with problem number 8. The sum from n equals 0 to infinity of 4 times negative 1.05 to the nth power. Let's write out the first few terms of this series. If n equals 0, what's the first term of this series going to be? 4, right? Because anything to the 0 power is 1. Plus 4. Now at n equal 1, I'll have negative 1.05 to the first power. And at n equal 2, negative 1.05 to the second power. And so on. What kind of a series is this? Anyone? Anyone at all? What kind of a series is this? Help me out. Geometric, yeah, thank you. It's a geometric because to get from one term to the next in this series, you're multiplying by negative 1.05. That makes 1.05, or excuse me, negative 1.05, the common ratio. There's a problem, though. There's a problem in terms of trying to find this sum. And that problem is that the absolute value of negative 1.04 is greater than 1. So what that's saying is that this infinite series doesn't add up to anything finite. It diverges. So therefore, we've seen this before, right? The little triangle dots, therefore, the series diverges. It doesn't add up to something nice and neat. Let's take a look at problem number 26. So the sum from n equals 0 to infinity of negative 1/5 to the nth power. So So kind of like the last one, let's write out the first few terms. Andrew C. What's the first term going to be when n equals 0? Yeah, just a 1. And then the next term at n equals 1, what would that equal? Yeah, negative 1 over 5. And then from there, negative 1 over 5 squared, and so on. What kind of a sequence, what kind of a series is this? Geometric. So it's a geometric series. Let's determine a few relevant facts. A sub 1 and R. What's A sub 1 here? A sub 1 is 1. A sub 1 is your first term. So here's our A sub 1. What's the value of R? Negative 1/5. Because that's what you're multiplying by to get from one term to the next, is negative 1/5. Great.
What if it was different than a 1? What if it was like,
Oh, it can be.
it can be any number?
Can be any number. Doesn't matter. In fact, a couple of problems come to mind here, and maybe we'll go through both of those. But in this case, what I can do then, because this is less than 1, absolute value of R is less than 1, that works, then I can find what I'll call S sub infinity. That is the entire sum here. Sum from n equals 0 to infinity of negative 1 to the 5th power. So it's kind of cool that we can do that. So that's going to be 1. Remember, it has the form of a sub 1 over 1 minus r over 1 minus negative 1/5. So that's going to be 1 over 6/5, which is 5 over 6. So that's your infinite series. That's your total. All right, let me do a real quick one here. Don't even copy it down because I want to do it really quick. But you ever notice how cities and maybe countries will compete for big ticket events like the Olympics or the Super Bowl? I mean, it's a big deal to land that, right? Because it brings a lot of money to your city. The reason they do that isn't necessarily quite as obvious as it might seem at first thought. Now, when the Super Bowl came to Detroit, estimates were that they spent $50 million. But that $50 million doesn't necessarily go into somebody's pocket and stay there. If you're spending it at the bar, you have to pay salaries, you have to buy food, you have to pay taxes, etc. So a lot of that money gets re-spent. So depending on the economist or the model, etc., let's say 80% of that gets re-spent. Now that money gets re-spent again, because when somebody buys food, they're going to have it delivered, they're going to have to pay somebody to deliver it, etc. So that money gets re-spent again. So $50 million re-spent again, times 0.8 squared, etc. And what is this? Well, this is actually kind of an answer to your question, Ted. This is an economic multiplier effect. A sub 1 is $50 million. What's R in this case? 0.8. Let's see if we can't figure out S sub infinity. What would be the total if this applied all the way down the line? If that kept on getting respent and respent and respent and respent and respent, it would be $50 million divided by 1 minus 0.8. And that would turn into $250 million. And that sounds a lot more impressive. Now, if this economic multiplier would be 0.9, then our math would have given us $500 million down here. So, but like I said, the reason that people compete for this is because it's a big shot in the arm to an economy. $500 million, $250 million, that's a big kick in the arm. So,
Is that really a shot in the arm to the service industry, though?
you know, I'm not an economist. I just know the mathematics behind it. So, I'm sure it's, yeah, I don't know how accurate it is, but it is something that economists do pay attention to. And it's literally called the economic multiplier effect. So, okay, let's get back to some of the problems here. Let's pick up with problem number 40, which is 0.215 bar. And we want to see if we can't write that as a fraction. So, first of all, let's remind ourselves what that 0.215 bar means. What that means is 0.215, etc. It's saying that that part here underneath the bar is the part that repeats itself forever. Now, if I wanted to write this as a fraction, here's what I could do. I could write that as 0.2 plus 0.015 plus 0.00015, and so on. So can you agree that I've just broken this up into little parts? Now, this part we're going to ignore for the moment, the 0.2 here, because it doesn't really fit the pattern. But this part does fit the pattern. What pattern am I talking about? It's a geometric series. If you're not sure with your geometric series, what you can do is you can take one term and divide it by the next. So you should get a constant ratio. And let's see if that's true. So let's take 0.00015, and I'll divide that by this one, 0.015, and I get 0.01. Okay, let's try these two. I should get the same thing. So this time it's 5 zeros divided by a leading of 3 zeros. So 0.0000015 divided by 0.123, 3 zeros and then the 1.5, and I still get the same thing. I'm still getting 0.01. So what that's saying is that this is a geometric series. What's a sub 1 for that geometric series? Yeah, 0.015. It's the first term there. So 0.015. What about R? R is 0.01. So the sum of this then, call it S sub infinity, is 0.015 divided by 1 minus 0.01. And let's see if it's probably going to give us 15 over 999 maybe. Let's take a look here. 0.015 divided by 1 minus 0.01. And then hit the math key, answer the fraction. Oh, 1 over 66. Okay, so that's 1 over 66. Almost done. What's 0.2 as a fraction? Actually, you know what? Doesn't even matter. Let's do it this way. Let's add plus 0.2, and now hit the math key, answer the fraction. And there you go. There's exactly the problem that you're looking for. 0.215, etc. And that turns into 71 over 330. Okay. Yes. How are we looking on problem number 40? You okay with that one? In the same manner that we just did the previous bunch, here's another one, kind of a freebie fast one for us. This sum, the sum from n equals 0 to infinity of 1 over 2 to the n. So there's going to be 1 plus 1/2 plus 1/4 plus etc. See if you can't figure out this infinite sum. This is not one that's in the book, although it could be. What would that infinite sum be? Bless you. So help me fill this in. Trevon, what's a sub 1? What's r? 1 over 2. S sub infinity is going to be a sub 1 over 1 minus r. 1 over 1 minus 2. Do we need a calculator for that one? What's that going to give us? 2. Yay. 2. So, an infinite number of mathematicians walk into a bar. And they pull up to the bartender, and the first one says, I'll have a beer. And the second one says, I'll have half a beer. The third one says, I'll have a quarter of a beer. And after a little while, the bartender stops him and he says, stop. And he pours out 2 beers. He says, here you go. You guys know your limits. All right. Cool. I can't tell that one's from any of my classes. So that was cool. Let's see. Are you getting pretty good with the infinite sums here? The geometric series? All right. Let's try some different stuff. So far, the only thing we really know how to work with is geometric series. You can tell if these geometric series are going to converge or not, the infinite ones, because if r is greater than 1, it's not going to converge. There's another way you can show that something won't converge. And this is probably the easiest test that people are going to get wrong on their exam on this stuff. It's called the Nth Term Test. In order for a series to converge, the terms eventually have to get really, really small. You can't add up an infinite number of large numbers and expect to get something finite. You just can't. So the Nth Term Test can show convergence. Nth term, or can show divergence. Term test. Maybe I should take the book's notation on this one. If the limit as n approaches infinity of a sub n is different than 0, unless these things are going to 0, this sum from n equals 1 to infinity of a sub n diverges. The terms in your summation have to get vanishingly small if you have hope that this sum is anything finite. Let's look at a couple examples, starting with problem number 10. The sum from n equals 1 to infinity of n over 2n plus 3 is what we're going to look at first. The terms in this series are here. So call it a sub n is n over 2n plus 3. Let's calculate the limit as n approaches infinity of n over 2n plus 3. What's that limit? All right, it is infinity over infinity. Sure. Yeah, it's going to go to 1/2, right? Now, you can pull out the heavy guns, the L'Hopital's rule, and end up with 1 over 2. All right, that's fine. Another way you can do that is you can, just divide everything by n. So this would be a kind of a college algebra approach. But I'm hoping that you're comfortable with it. If I multiply the numerator and denominator by 1 over n, I'll get 1 over 2 plus 3 over n. And eventually, as n goes to infinity, this term's going to go to 0. So we get 1 over 2. There's a problem with that, though. It's not 0. Because this is not 0, essentially you've got an infinite number of terms that are getting close to the value of 1/2. If you add up 1/2 plus 1/2 plus 1/2 an infinite number of times, you're not going to get 0. You're not going to get something that converges. Actually, it doesn't matter if it's 0. You're not going to get something finite. So therefore, the series diverges by the nth term test. Let's try another one. Problem number 42. The sum from n equals 0 to infinity of 3 to the n over 1,000. 1,000 is a pretty big number, but we'll see here. Here's your a sub n. Is 3 to the n over 1,000. Can I apply L'Hopital's rule in evaluating this limit? No. But do I need to? Not really. 1,000 is kind of a constant, so I can pull that out in front. What's the limit as n approaches infinity of 3 to the n? Infinity, right? It's just going to get really big, really, really fast. It's not quite the supernova of functions, but it's close. So, infinity. At the very least, I can say that that's not equal to 0. And because it's not equal to 0, it's going to diverge by the nth term test. So therefore, the series diverges by the nth term test. The one place where people are going to really, really stumble is this. The nth term test cannot show convergence. Just because something passes the nth term test doesn't mean that it'll converge. It may not. It's just going to depend on the sequence or the series. But this is going to be the biggest challenge for you in using the nth term test. You can only use it to show that something diverges. It will not prove that something converges. And a great example is this one. The sum of n equal 1 to infinity of 1 over n. This is a very famous series called the Harmonic Series. And the Harmonic Series passes the nth term test, right? If you took a look at the limit as n approaches infinity of 1 over n, what would you get? 0. So it passes the nth term test. This series plagued mathematicians for a long time. I want to say at least 100, 200 years. They didn't know if it converged or diverged. What do you think? Converge or diverge? Is that eventually going to add up to something small, something finite? No. But it converges so incredibly slowly. It's amazing. I mean, I think if you go out to like a billion, if you added up the first billion terms, that total would be like 14. Now think about what it means to diverge. Diverge means that total is going to get arbitrarily large. It means you can name any total that you want, and it's going to get bigger than that total. And yet, after a billion terms, it's only going to get up to 14. Somehow or another, if you keep on adding more and more terms, you'll get as high as you want. You can get over a trillion. You can get over a quadrillion. But it converges incredibly slowly. So this is a nice example of something that passes the nth term test but doesn't converge. It diverges. We'll learn some more ways to test that in a little bit.
So when something diverges, it doesn't have an answer.
Correct. When it diverges, it really means that it totals up to something that either is infinite or we can't calculate. It's not going to settle down to anything. It diverges means that this total is effectively infinite.
So the one you were showing us, that converges, right?
This one?
Yeah.
That one diverges. And this is a great example of this part right here. It passes the nth term test, but the nth term test can only show divergence. It can't prove something converges. Just because it passes the nth term test doesn't mean it converges. And this is a nice example showing you the opposite of this. Doesn't hold. Okay, a couple more from this section. Problem 46. We're going to look at some things that are called telescoping series. We'll start with problem number 46. The sum from n equals 1 to infinity of 1 over n plus 1 minus 1 over n plus 2. Okay. Our approach here is that we're going to take a careful look at the sequence of partial sums. So let's look at the sum of the first couple terms here. Let's start with, say, s sub 2, which would be the sum of the first two terms. So that's going to be 1 over 2 minus 1 over 3 plus, at n equal 2, that'll be 1 over 3 minus 1 over 4. Now I'm not going to try and get too fancy here in my mathematics and my simplifying things, but I will notice this. Those two terms cancel each other out, right? We got a plus 1/3 and a minus 1/3. Let's look at s sub 3. So the only difference now is that I'm going to add on the next term from this series. So when n equals 3, what am I going to get here? 1/4 minus 1/5. And again, we get some nice cancellation here. Those two terms cancel, but we get some more bonus cancellation, right? What else cancels? The 1/4 cancels. Now let's start taking a look at what's left. I have 1/2 minus 1/4. Here I have 1/2 minus 1/5. And there's kind of a pattern here. And I don't know, do you need should we look at one more maybe? Maybe S sub 5 or something like that? Can you try and figure out what's going to happen when I look at S sub n? The nth term. It's going to be 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4. All the way down to the nth term. Now what's the nth term going to be? Well, it's just going to be this at n. So it's going to be 1 over n plus 1 minus 1 over n minus 2, or plus 2. The question is, what's going to be left? Good. These terms are going to cancel out, and the pattern that you can and should be seeing is that what's left is just the first and last terms. So those cancel each other out, and then I'd have these canceling each other out. So that gives me 1/2 minus 1 over n plus 2. That's S sub n. Now how does that help me? Well, that's the sum of these terms all the way up to the nth one. But this is really S sub infinity. It's the sum of all those terms. The fix here, to calculate this, S sub infinity equals the limit as n approaches infinity of 1/2 minus 1 over n plus 2. Basically, it equals the limit of S sub n. So as we let n get bigger and bigger and bigger, then that's going to get closer and closer and closer to the overall sum. What's that limit? It's 1/2. Yay. That's going to disappear. Your limit's going to equal 1/2. Let's see, images. All right, so let's see. It's called a telescoping series because just like an old pirate's telescope, the series kind of collapses on itself. And we saw that when we were looking at this part right here. All these terms canceled each other out evenly. So you're just folding this in like an accordion, or better yet, a telescope. So when it collapses on itself like that, you can take its limit of S sub n and then calculate the exact sum of the series. So unlike some of these, we actually know what the sum of this series is. The sum of that series is 1/2. Let's try another one kind of like that. Are we okay with problem 46? There would be a term before this that would cancel with it. So the pattern from up above is that everything's going to cancel except the first and the last term. So you kind of have to go through this with several of these. Let me do S sub 4 really quick. It'd be 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1/4 minus 1/5 plus 1/5 minus 1/6. So again, what you're going to see is a lot of collapsing of all these terms. These cancel. These cancel. And then these cancel. So consistently what you're left with is the first term and the last term. So sometimes it takes some careful playing around with these things to see how they're going to collapse, but if it's a telescoping series like this, it will collapse on itself. Okay? So, good question. Anything else on problem 46? Let's try problem number 54. Sum from n equals 1 to infinity of the ln of n plus 1 over n. Okay. Well, let's start out by using a little property of logarithms. What can I do with the log of a quotient? Thank you. ln of n plus 1 minus ln of n. Cool. So all we did was we broke it up using the quotient rule. So let's take a look at the first few expressions here. Let's start with s sub 3. S sub 3 is going to be, let's see, ln of 2 minus the ln of 1 plus the ln well, you're starting out here at n equal 1. So if I put in a 1 here, 1 plus 1 is 2. So I get the log of 2 minus the log of 1. Okay, it's all right. We'll get up to what you're saying, though. So at n equal 2, this is the log of 3 minus a log of 2. And then at n equal 3, we get the ln of 4 minus the ln of 3. And that's where we're going to stop. This is s sub 3 is going to be the sum of the first 3 terms. Okay. So ln of 1 is 0. Don't have to worry about that. But let's see what kind of things cancel. What do you see that cancels? There's an ln of 2 and a minus ln of 2. They cancel. What? Ln of 3 and minus ln of 3. And what we're left with is kind of part of the first and part of the last term. We're left with minus ln of 1, which is 0, plus ln of 4. Now maybe if you're good, you can figure out the pattern from here. Maybe you need one more example. It's up to you. Let's take a quick look at s sub 4. So for s sub 4, it's going to be ln of 2 minus ln of 1 plus ln of 3 minus ln of 2 plus ln of 4 minus ln of 3 plus ln of 5 minus ln of 4. Let's do some cancellation here. Ln of 2 and ln of 2, they cancel. What else can we cancel? Ln of 3 and ln of 3. And ln of 4 and ln of 4. So again, what we're left with is this first term minus ln of 1 plus ln of 5. So we have to figure out, what does S sub n look like? What's that pattern going to look like in general? All right, so it's going to be the first term minus ln of 1, which of course is 0, so we don't really need that. And then this last term here. Now what you have to correspond, and I think Hans has got it, with is this. We had a 3 here, we got a 4 here. 4 here, 5 here. There you go. Thank you, gentlemen. Minus ln of n plus 1. So this can be thought of as the limit, as n approaches infinity, of S sub n. And since this is just a 0, let's call that ln of n plus 1. The limit as n approaches infinity of ln of n plus 1. What's that limit? Infinity. Yeah. Basically, it diverges. Although, even though it diverges, it does actually pass the nth term test, because those terms are going to 0. Essentially, it's going to the log of 1. Log of 1 is 0. So even though these terms go to 0, the sum does not go to 0. The infinite sum doesn't go to 0. So it converges to infinity. It diverges. Therefore, it diverges. Okay, almost done with this section. Just a couple more quick ones. Let's look at problems. Let's see. Let's do problem 62. Kind of twisting things around a little bit for us on this one. Was there any other comments or thoughts on 54 before we move on that one? Doing okay there? Rand? Look like you're... No? Okay. All right. Problem 54 gives us the sum from n equals 0 to infinity of 2 over x raised to the nth power. Now, if you were to write this out at n equals 0, you would get a 1. At n equal 1, you get 2 over x. And then at n equal 2, you get 2 over x squared. And so on. What kind of series is this? Geometric. So it's almost a trick question, right? Because there's only one series that we really have a name for. It's a geometric series. So, yeah, kind of like the old joke about the Model T, right? Whatever color you want, as long as it's black. I mean, that's all they made the Model T in. So, all right. So it's a geometric series. The question is, what values of x would make this converge? Well, in order for this to converge, what has to be true about r? What's the condition for an infinite geometric series to converge? Absolute value of r has to be less than 1. So, okay. What's the value of r for us in this case? 2 over x. If you solve this equation, then what it equivalently works out to is negative 1 is less than r is less than 1. And for us, r is 2 over x. Over x. So we got to solve for x. Trying to think of the most efficient way I can solve for x in this case. It's not a squeeze theorem. Boy.
Just gonna do the old way.
What's that? Is you can just
Like intermediate algebra.
no. What I really want to do is I really want to take the reciprocal of like everything. But I know that it would actually work in this case, but I'm not really comfortable doing it. So what else can you do? Yeah, it's a good question. What would you do in a case like this? I mean, we could solve them one at a time. All right, look, I don't want to spend too much time on this. What has to happen is that this ratio has to be less than 1 and greater than -1. So what's the most that 2 could be and still be less than 1? Well, it means x has to be less than 2 on one end and greater than -2 on the other end. So you can, I mean, it is going to give you the right answer if you take the reciprocal on both sides. I'm going to have to get back to you as to exactly how I'd recommend for you to solve that. I'm not really comfortable saying take the reciprocal on both sides, although I can see it works here. I'm just not up to that one. So that's your value of x. As long as x is between -2 and 2, then, you know what? That doesn't. No, that doesn't work. No, it doesn't work. We'll tell you what. Let's solve it a different way. We've got the absolute value of r is less than 1, so it's going to be 2 over x is less than 1 in absolute value. There's two possibilities here. Either 2 over x is less than 1, or the negative possibility is that -2 over x is less than 1. Boy, these are becoming more of a pain than I realized. Well, the way to do this is to get 0 on one side, get a common denominator. Wow, my bad, I didn't realize this. 2 minus x over x less than 0. I'm sure you've got a video on YouTube. It's for my math 1150 class, section, what was it, 10.3 or 10.4? 10.4, right? No, 10.4, where we did quadratic and rational inequalities. That would discuss doing this. You would have to set up a real number line, 0 and 2. Wow, this is really, really bad. Yeah. All right. It's just a really big problem. Yeah, it's another one that's on the test. Gosh, I didn't realize that this was going to be so nasty here. No, what's going to happen is that this number is actually going to have to be bigger than 2, right? It's going to be bigger than 2. That'll make the ratio less than 1. So these are the numbers that we want to exclude. We want to exclude -2 to x less than 2. You want to get everything on the outside of that. So it's going to be -infinity is less than x is less than 2, or like -2, or 2 is less than x is less than infinity. Boy, I just didn't realize that there was a ton of work here in actually solving this correctly. So my bad. Didn't look far enough ahead at that one. I just said, oh yeah, it's a good one. The point of it though is pretty good, and that is we want to make sure that this ratio is less than 1, and that's going to be less than 1 when the number is outside the value of -2 to 2. We'll see more of those in a better form a little bit later in the book. For right now, We're going to skip those problems. And let me give you some homework. For homework, try 1 through 19, 23 through 51, and that's section 9.2. Okay, let's take a break.